Okay, welcome back. So now, today, we're going to do graphs for quantitative data. Okay, so what are we talking about? We're talking about numerical data. Remember, quantitative is numerical data. So, this is going to be probably a little bit longer than the last one, okay, because we're going to go through several different types of graphs. Okay? So the first graph, which is the most common one that we're going to talk about, I'm going to probably spend the most time dealing with this one, is the histogram. And so what I'm going to do is I'm going to construct the histogram using a couple of rule of thumbs and things like that, and I'm going to show you how to construct it. So again, this is going to be based off of what we've already done in a couple of sections ago when we started doing frequency distributions, okay, grouped and ungrouped. This would be where you would do a grouped frequency distribution. Okay, so you can create a histogram off of any grouped frequency distribution. Okay, if it's an ungrouped frequency distribution, it would be the same as a bar chart. Just instead of categories, you'd have tick marks for each number. Okay, so a bar chart would be used for categorical data that would be discrete and that would have a short range. Okay, so that way you just have bars. Histograms are used for grouped frequency distributions, and so that's what I'm going to start with. Okay, so again, this is going to be, I'm going to use the example on page 49 of the textbook, okay, because this is going to have 100 numbers in your data set, 100 values in the data set. I'm not going to write that on the board. So again, so use the example on page 49 and follow along, okay? Okay, so now I'm going to write out the grouped frequency distribution for this data set. Okay, so that's where I'm going to start. So probably could be good practice to create the grouped frequency distribution yourself for this assignment. But again, in the example, it already has it for you, so if you can want to follow along, you can. Okay, so let's start. Okay, so it says the following data are the heights in inches to the nearest half inch of 100 male semi-professional soccer players. The heights are continuous data since height is measured. Remember, height is a continuous data, continuous variable, right? So we're going to construct the grouped frequency distribution, okay? Now, the range in this data set is 14, bigger than 10. Okay, so we're going to group this together. Again, it's continuous. The range is bigger than 14 or bigger than 10. A couple of rules of thumbs before I get started. So one rule of thumb is that when you want to use a histogram, this is a simple rule that usually works in most cases, is we want to use a histogram if we're dealing with large data sets. Typically, anything 100 or more, we're going to want to construct a histogram. Okay? Most of the data sets that we're going to use in this class to construct a histogram is going to be less than 100. But again, that's just a rule of thumb. In the real world, we would construct the histogram for large data sets only. Okay? Not for small data sets. So anything 100 or more, we would do a histogram. The other thing too is one of the key characteristics of a histogram is that all of the classes are contiguous. Okay, all of the bars are contiguous, which means right next to each other. They're adjoining, okay, and there's no gaps. Okay, so one of the key aspects I talked about before is there's no gaps. Okay. Okay. And we're also now going to introduce something else called a class boundary. Okay, so once you have the class limits, to construct a histogram, all you need to do is add to your frequency distribution are class boundaries, because you already have the class limits. Once you have your frequency distribution or your relative frequency distribution, all you have to do is add class boundaries and you can immediately construct your histogram. That's how easy it is. Okay? So I'm going to take the table on page 49 and I'm going to construct how I would do the table so that I can add the class boundaries easily, okay? So, let's see here. So again, let me write out, I forgot to put this title on for today. So graphs for quantitative data. Okay, so here's the example. Oh, let me write histograms for the title. So first one we're going to talk about a histogram. Histograms. Okay, so we're going to use example page 49. Okay. Okay, and here's the table for the 100 soccer players, semi-professional soccer players, for their heights. This is table represents the 100 heights. Okay, so here's what we have. So this is going to be my table that I would construct. Okay. Now this is not the way they construct it, but this is the way I would construct it. Okay, and this is the way I would encourage you to construct it as well. Okay, so here is, I'm going to put the class limits in first. So here's the lower class limit, and I'm going to abbreviate it as LCL. So LCL, lower class limit, upper class limit, and this is going to be frequency, and this is going to be relative frequency. Okay? And so now, the lower class limit is 60. And what they did was they ended up constructing 8 classes, which is fine. So here's what they came up with, 8 classes, okay? So they got 60.0 to 61.9. Now note, let me write out the table and then I'll talk about what they did here, which is going to be important. 62.0, I'm just going to write these out. 64.0, 66.0, 68. So they're going by 2s. So the class width we know is 2 on this, in this case. So this is 6 feet right here, because this is inches. Remember, these are in inches. Okay, so here's the table, and the upper class limits, 61.9. So again, the class width is 2, so we can easily get these now. So 61.2, or 61.9, 63.9, 65.9, 67.9, 69.9, 71, or excuse me, yep, 71.9, 73.9, and 75.9. Okay, so now if you look, if you look at the data, now the data in this example is great because they actually have it ordered from least to greatest, so you can easily check to make sure all the data is in there in these classes. So the lowest one is 60, so 60 is in there. The highest height they have is 74. So 74 is definitely in there. So we've got all the data covered, okay? So now here are the frequencies. And now remember, the frequencies all have to add up to the sample size. What's the sample size? We know n is equal to 100. The sample size is equal to 100. So this frequency must add up to 100, okay, which it does, okay? Now, the relative frequencies, remember how to calculate relative frequencies. All we're going to do is take each one of these frequencies and divide by the sample size, which is 100. So all we're going to do is move the decimal point to the left 2 spots. So this is going to be 0.05. Or you could write these as percentages too, but relative frequency technically is a decimal, but we normally write it as a percentage. But again, in the example, they leave it as a decimal, which is fine. Okay, so this is 0.05, 0.03, 0.15, 0.4, 0.17, 0.12, 0.07, 0.01. And of course, if this sums up to 100, obviously this is going to sum up to 1.00 or 1. Okay, so we're good. These are our checks. We always want to make sure we do our checks. Okay, so now this is the way I would construct my table. Why do I have the blank columns? Because that's where I'm going to put the class boundaries. So this is going to be the lower class boundary. I abbreviate LCB. And this is going to be the upper class boundary. Okay, now before I do that, let me go back to something that they did, because I want to explain this further for your understanding. Notice how the data, if you look at the data goes out to 1 decimal place. So let me show you how they did the class limits. Notice that the lower class limit was the minimum value, like I talked about. Well, if you go up by 2, because they wanted 8 classes, so the class limit they found out was 2. So if you go up by 2, you go up to 74. Now, how do you get to the next lower class limit? Well, before, what did we do? We subtracted 1. But why did we subtract 1? We subtracted 1 because we were talking about whole number values. Okay? Here, we're going out 1 decimal place. So when we go to find the upper class limits, we're not going to subtract 1 from the lower class limit. We're going to subtract 0.1. Does that make sense? Okay, so how do I get the first upper class limit? I subtracted 0.1 from 62, which gave me 61.9, and then all I did was add 2 to the rest of them, to get the rest of them, okay? So again, depends on how many decimal places the original data set goes out to, okay, the values, okay? So I wanted to make that comment on it, okay? So note that for your own reference. Okay, so now, how do I get the upper and lower class boundaries? Well, you have to understand what a class boundary is. The class boundary is solely used for constructing the histogram. The class boundary is where the bars are going to touch, okay? Because if you notice, we're always going to have a gap in our table between the upper class boundary of one class to the lower class boundary of the next class. So in this case here, we have a gap of 0.1, right? Which should make sense, because we subtracted 0.1 to get there, to get that class limit, okay? How are we going to close that gap for getting for constructing the histogram? Well, that's where the class boundary comes in. What we're going to do is we're going to find the midpoint between the two. Well, what's the midpoint? It's the halfway point between this class and this class. So between the two classes. So we're going to take the gap, which is 0.1, and we're going to find the halfway point. Well, what's the halfway point between 61.9 and 62.0? Well, let's find out. Well, the halfway point, so the class boundary if we take the upper class limit, right, of one class, not upper, okay, so pick a class. Pick an upper class limit. It doesn't matter. Okay? Pick an upper class limit of a class, and then add that to the lower class limit. In fact, let me write it this way. Since I'm using abbreviation, it'd be better. So use the upper class limit of one class, okay, and add that to the lower class limit of the next class, the following class, of the next class. And then take those two, add them together, and divide by 2. So basically what you're doing is you're finding the midpoint between two classes. Okay, that's essentially what you're doing. Okay, so you're going to pick a class. So it doesn't matter which class you use. So let's use this class here. Okay, because it doesn't matter. I would typically use the first class. Okay, but it doesn't matter. In fact, well, let's just use the first class. Okay, but it doesn't matter which upper class you use. So let's use the first class. Okay, so what's the upper limit of the first class? 61.9. So 61.9. And so now what we're going to do is we're going to add the lower class limit of the next class. Well, what's the next class? This one. So we're going to take the lower class limit, 62. So we're going to take that, 62. We're going to add those and divide by 2. And what do we get? We get 61.95. Okay? Hopefully you can see that. Let me, because I don't know if you can see that or not. So this is going to be 61.95 is going to be the midpoint. Okay? So now, this is going to be the upper class boundary. Okay? Between this and this. So this is going to be 61.95. Okay? So another thing to note is that what are we essentially doing? We're finding the midpoint of between these two. So what are we doing? Well, we know it's 0.1. The gap is 0.1. Well, what's half of 0.1? 0.05. So what are we essentially doing? We're adding or subtracting 0.05 to each of the class limits to get the class boundary. So watch this. Well, how do I get the class boundary for all of these? I'm going to subtract off 0.05. How am I going to get all of the class boundaries over here? I'm going to add, or not 0.5, I'm sorry, I think I said 0.5. I'm going to subtract off 0.05. Okay? Because what's half of 0.1? 0.05. That's what I meant to say. So I'm going to subtract off 0.05 here. I'm going to add 0.05 to get the upper class boundaries here. That's essentially what I'm doing when I find the midpoint, okay? Now, I can do this calculation all the way down. I wouldn't do that. There are two ways you could think about this. One way is just what I explained. What's the halfway point between these two? Well, I know the gap is 0.1, right? That's what I subtracted to get these. So what's half of 0.1? 0.05. That's what I'm going to use. I'm going to subtract off 0.05 here to get these class boundaries. I'm going to add 0.05 to get these class boundaries. That's one way of doing it. The second way of doing it is using class width. So I can use this formula to get the first one. Once I have the first one, I just add the class width to get the rest of them, which is 2. So I can add 2 to this one and get the next one. So this would be 63.95. And add 2 more to get the next one, 65.95. Notice what's happening when I add 0.05 to this. I get the same thing. So I can, either way will work. Either way, okay? So if I keep doing this and I add 0.05 to this, I'm going to get 67, or add 2, so I get 67.95, 69.95, 71.95, 73.95, and 75.95. And now if I subtract off 0.05 here, look at this. If I subtract off from here, the 62, all the way down, I'm going to get the same as these. From 62, if I subtract off 0.05 from 62, I get 61.95. So all of these will be duplicated over here, starting with the second class. So here, it's going to be 61.95, and then I can just start adding 2 all the way down. So it would be 61.95, 63.95, 65.95, 67.95, 69.95, 71.95, and the last one will be 73.95. Okay. Now I just have to get the first one, which is just 0.05 minus this, which is 59, or subtract 2, 59.95. And I'm done. Now I've got my full table. Okay, now this is what I'm going to use to construct my histogram. Okay, and I can construct either a frequency histogram or a relative frequency histogram. The only difference is what is going to be on my x-axis. I'm either going to have frequency as my x-axis or relative frequency as my x-axis. Either, that's the only difference. Okay, so here's what I'm going to do. I'm going to use this table and I'm going to construct the frequency histogram. So again, pause this or use the page on 59 to follow along. Okay, so I'm going to erase this. Again, this is how I would construct my table instead of what they did in the book. Okay, it's a little less work, and everything is on one table instead of 2 tables. Okay? Okay. So now, I'm going to use this table to plot 2 things. I'm going to use frequency as an example. I'm going to plot frequency on my x-axis, and I'm going to plot my class boundaries. Or actually, I meant to say y-axis, not x-axis. I'm going to plot frequency on my y-axis, and I'm going to plot class boundaries on my x-axis, and then we'll be done. Okay? So let's do this. So here is where I start. So what I'm going to do is, again, I want equal widths for my classes, right? Remember, classes must be equal widths. Okay? So I'm going to start by just doing my tick marks and make them equal widths. Okay? So I want 8 classes. Okay? So I want 1, 2, 3, 4, 5, 6, 7, 8. So I got 8 classes here. Okay? Now I'm going to put a break in the graph. What does the break in the graph mean? All this break means is it's telling my audience that I'm deleting part of the graph for room, okay, for the sake of room, okay? Because what's the lowest value of my data set? 60. Okay, so I don't want to start my graph at 0. So if I start my graph at 0, I always want to start my graph at 0, but I don't want to put a big gap from 0 to 60 in my graph. So what I do is I put a break in the graph and just let my audience know that I'm deleting part of the graph in my display. Again, it's for reading purposes. Okay, so here's my classes. Now what I'm going to do is I'm going to put the class boundaries here. Okay, so the class boundaries start with 59.95. So this is going to be 59.95, and then what I'm going to do is I'm going to go up by 2, the class width. Remember the class width. So now I'm going to go up by 2 for the next class boundary. So it's going to be 59.5, 61.95, and I'm writing the numbers vertically or at an angle to give myself room. You'll see that a lot. 61.95, 63.95, 65.95, 67.95, 71.95, 73.95, 75.95. Hold on a second. Did I get this right? 59, 61, 62. I knew I missed one. 67 to 69. 69.95, 71.95, 73.95, and now 75.95. Okay? Okay, so now I got everything marked. Now what I'm going to do is I'm going to put frequencies. Well, the frequencies, if you look at the frequencies go from 1 to 40. So in this case here, I'm going to do my frequencies by 5. So each tick mark is going to represent 5. Okay? So again, you have to determine what would be the best increment when you look at these. So I'm just going to do mine by 5. I'm going to start at 0 and go to by 5. So okay, so there it is. So I'm going to go 5, 10, 15, 20, 25, 30, 35, 40, 45. Okay, so now I've got my table, I've got my graph set up. Now all I have to do is put in the bars. This is the easy part, okay? So now all I have to do is go by the table and go by the frequencies. So the first class has a frequency of 5, okay? So what am I going to do? I'm going to go from this boundary to this boundary. So this is the first class. So I'm going to go up to 5. And across. There's my first class. There's my first bar. Now the second bar goes to a frequency of 3. So it's going to be a little bit shorter. So what I'm going to do is I'm going to estimate about 3, which 3 is going to be right there, and I'm going to go across to the next boundary. Okay? Notice how my bars are touching, no gaps. Okay? And now the next one is 15. So now I'm going to go up to 15, so I'm going to carefully draw this. So I'm going to go up to 15. And so there's the next bar. And now the next one goes all the way up to 40. So I'm going to start here. I'm going to go up to 40. And the next one is 17, so I'm going to draw my bar up to 17. Okay, and you just do the best you can. So this will go to 12. So again, I'm going to go over to 12, so about right there. And then the 7, which is going to be, let's say about right here, and then 1 is going to be right there. So there's my histogram. I'm done. That actually ain't bad. I like it. So now the cool thing is now you can look at the shape of the distribution, which is what we're going to talk about next, is you can talk about the shape of the graph. Now, the only difference between this relative frequency histogram, or excuse me, this frequency histogram and a relative frequency histogram is what do we put here? In a relative frequency histogram, instead of frequencies, we would put relative frequencies here. So this would go from 0 to 100% or 0 to 1, depending on how you wrote the relative frequencies. Okay, that's it. Okay, and in fact, if you were to plot both of them together, you would see that the distribution for both of them would look exactly the same, virtually identical. Okay, the only difference would be the scale. Okay, so now a couple of things here. Let me go on. Let's see here. Okay, I am going to show you how to do this on the calculator. Okay, so, but before we do that, let me talk about shapes of distributions. Okay, and I think this is a good shape to do. Okay, I was going to do it later, but let me do it now. Let me see here. Do I do this now? Yes, let's do it now. So there are 4 different shapes that we're going to talk about when it comes to histograms, or any kind of distribution, okay? But histograms is a nice, easy way to do it. So now, one of the things that you can see in this histogram is, well, we obviously know that the majority of the heights of these semi-professional soccer players is around between about 66 and 68 inches, okay? So what is that in feet? Well, you're talking about, what? 5 feet? So a little over 5 feet, 5.5 feet tall, because 5 feet is 60, well, let's see, 60, so you're talking about, yeah, between about 5.5 feet tall, okay? And look at the distribution. Okay, so you have the majority of soccer player heights, semi-professional soccer player heights here, and then you've got some over here and you've got some over here, but it looks like you've got more over on this side of the middle than you got over here. And so what we're going to talk about is different distributions and how we can describe different distributions. So here are the 4 ways you can describe a distribution, the shape of the distribution, okay? So the first thing is we talk about symmetric, okay? Symmetric is where the left side looks like the right side. So if you look at the middle, the left side and the right side virtually are the same, okay? That's what we call a symmetric distribution. So it looks like a nice bell-shaped curve. Okay, sorry about that. So it looks something like this. You know, in a histogram, it would look like a bunch of bars, but I'm just going to write it as a smooth curve, so it looked like something like this. A nice symmetric curve where if you drew a line down the middle, the left and the right side look virtually the same. Okay, so this would be an example of a symmetric distribution. The other type of distribution is called skewed, okay? Skewed is just another way of saying not symmetric. So skewed are two types of skewed distributions. You have left skewed or right skewed. So left skewed is where the tail on the left is bigger than the tail on the right. So you have more data to the left. You have extreme values or more data to the left than to the right. Okay? Okay, so it would look something like this. Oops. Ah. I don't like the way I'm drawing this. Okay, so let's do. Like that. Okay, so here's the distribution where the middle is about right there. And so it's obvious that the data is skewed to the left. So this would be an example of left skewed. Or another way of saying it is negative skewed. Because the tail is bigger in a negative direction versus positive, right? Okay. And obviously the next one, if you haven't guessed already, is positive skewed or right skewed. And that would look something like this. Where here, the middle is right here, and obviously the tail on the right, bigger than the tail on the right, or the left, okay? So this would be right skewed, or what we call positive skewness, okay? Those are the three so far. The last one that we're going to talk about is another type of distribution that we're going to talk about later. It is symmetric, but it's a specific type of symmetric distribution. So, that is what we call uniform. And a uniform distribution pretty much looks like this. Looks like a rectangle. Okay, so a histogram that looks like this, or close to looking like this, is what we call uniform distribution. Okay, so again, those are the four different descriptions, or how do we, four different ways you could describe the distribution or the shape of a distribution. Okay, okay, so that covers histograms. Okay, so now let's talk about other types of graphs. The next type of graph that we're going to discuss is called a stem and leaf diagram, a stem and leaf plot, a stem and leaf graph, however you want to call it. Different texts call it different things, but it's a stem and leaf graph. Okay? What does this mean? Well, it's another way of describing data or using data to describe a distribution. Very similar to a histogram, but it actually uses the data to construct the graph. Okay? So let's look at what that looks like. Let's see here. Okay, so let's use this example here. Okay, again, I'm going to use this example. It says for Susan Dean's pre-calculus class. So this is a pre-calculus class. The scores for the first exam are as follows. Okay, so here are the exams. So here are the exam scores. And it's in increasing order. So again, this is very helpful. Okay, you're not always going to get data that's nice orderly like this. So again, you're going to want to organize the data to do this. Okay, easier, okay? Or you could do it without it by crossing off, but again, it's up to you how you want to write it. So this example gives it to you in increasing order, so it makes it easier. Okay, so there are the numbers. And I have, how many numbers do I have? I have so 30 numbers. So how many numbers do I have? So 10, 20, 30. Okay, so I have 30 numbers. Okay. So now what I'm going to do is I'm going to show you how to construct a leaf assembly diagram by example and leave it to you to understand it. Okay, so hopefully after this you'll understand what I'm doing. Okay, the first thing I need to do is understand what the stem is and what the leaf is. The stem is what I'm going to choose based on what the data is in. So what do I got? I got numbers that are in the tens. Okay, so here, since I've got numbers from 10 to 100, I'm going to divide each number into two parts, the tens column and the ones column. Okay, so the stem of my diagram, of my graph, is going to be created using the tens column for every observation, every number. The leaves are going to be constructed using the ones column for every observation. Okay, so here's how you construct a key. So I need to first do my key. Okay, for example, if I use 88, right? So 88, so here's my slash. What does this mean? The stem, right? So this is the stem. The stem represents 80. The leaf represents 8. So this would represent 88. Understand? So this is the key that I would put on my graph to let my audience know how to read my table. Okay? So that's what I'm going to start with. Now with this in mind, now I'm going to construct my graph. And once I show it to you, this will make perfect sense. So I'm going to draw a vertical line. So just like that. And so on this side of the line is going to be my stem. So this is going to be all of my tens columns. So what's the minimum value? 30. 33. What's my maximum value? 100. So I'm going to put all of the digits from 3 to 9 for the tens column. So I'm going to start at 3 and go down to 10. So it'd be 3, 4, 5, 6, 7, 8, 9, 10. Okay? So now on the right side of the line are my leaves. So all of the ones digits I'm going to place in the leaves. Now how am I going to do that? I'm going to do it by increasing order for all of the ones digits of every single observation. So on and so forth. okay? So now, for the 30s, so anything in the 30s, I'm going to go from 0 to 9, okay? So I've got a 3. That's the only 30 I have is a 3. So I'm going to put a 3 here. And so now you can see that this represents 33, okay? Now I'm going to go to the 40s because I don't have any more digits, okay? So that's gone. So the next one is I have the 40s. Well, I have 42, 49, and 49. So I have two 49s, which means I'm going to have 2 9s on the right side of the line. So the way I would write this is I would put 42, so 2, and then a 9, and then a 9. Get it? So now, 4-2 represents 42. 4-9 represents this 49, and then 4-9 represents this 49. Understand? Okay, so now what I'm going to do is I'm going to continue on and fill out the stem and leaf diagram, and at the end, you're going to see basically a histogram. Just rotated 90 degrees. Okay, so the 5s, I'm going to have 3, 5. So that's, I'm going to have 3, 5. And what I'm doing is I'm being careful to make sure that all of the numbers line up. Okay? So 3, 5. Now I got 6s. So 1, 3, 7, 8. So 1, 3, 7, 8. And then I've got another 8. Right? So I've got another 8 to put here. And then I've got a 9. I've got 2 9s. Okay, so now I'm done with the 6s. Now I go to the 70s. So I got 2, 3, 4, 8. So 2, 3, 4, 8. Okay, notice how I'm keeping everything in this right columns. Okay, so I'm done with the 70s. Now I go to the 80s. I got 0, 3, 8. 0, 3, 8. 8, 8, and I'm done. So I put 2 more 8s. 8, 8. Okay? Now I'm in the 90s. 0, 2, 4, 4, 4, 4. I got 4 4s. 0, 2, and 4 4s. So 0, 2, 4, 4, 4, 4, and then 6. Okay? And then the last one, I've got a 0. Because remember, I split it down 10 and 0, so that I got 0. So notice, I'm done. Now notice how I get a nice distribution. So a couple of things, again, I'm going to, as far as interpretation, look at this. I've got a distribution that looks something like this. It does, something like that. Okay, or I could do it this way here. Let me do it again. I can do this. Okay, let's do it this way. Let's say I'm doing, it's more, like that, maybe. Okay, now look, I got 2 peaks here. Okay, so it looks like I've got it skewed up or down because these are lower numbers. It's skewed to the left or negative. Okay. Also, I've got these 2 peaks. These are what we call modes. M-O-D-E, modes. So this has 2 modes. Okay. So bimodal. 2 modes is usually what we call bimodal. Okay. So look at that. So something's going on here because we've got a mode here and a mode here. This, we'll talk about this later, but this could be an indication we have 2 different populations. Okay. Another thing it could mean is that, hey, there's something going on here. I've got a huge I've got a large group of students that got in the 60s, got around a D, and I've got another group of students that got A's, okay? Now, this could be an indication that there was an outside influence on the data set. Now, this is too small of a data set to do that, but if I had a large data set, this would definitely be an indication that something was going on. For example, cheating. Okay. Now, for this small data set, that would be probably not probably something else going on. Either you've got a group of students that outperform, so you've got a bunch of A's and you've got a bunch of D's. Okay. Something to investigate. Okay. There's an interesting YouTube. Do a YouTube search on cheating, and there's this one professor, I forget what example, but he taught on a huge lecture hall. And he got this bimodal distribution. And as a statistician, I loved it because he goes into great detail on the analytics, and he basically caught the entire class cheating on the exam. It's a fantastic video, but he shows how, by using the analytics and the distribution, now he had close to 150, 200 students, so this is definitely a large sample size. So again, something like this you would not expect to occur on a large sample size for an exam. Okay, you would expect a nice bell-shaped type of curve, okay, or at least unimodal. That's the main thing. One mode versus two modes. Okay, so again, just something to consider. Okay, so this is how you construct the seven-leaf diagram. Okay, let's see here. Okay, the next thing we're going to talk about, line graphs, okay? So the typical line graph deals with bar graphs. Think of a bar chart, okay? A line graph typically is with categorical data or numerical data where it's ungrouped, okay? So think of the difference between grouped and ungrouped numerical data, okay? Okay, so line graphs used for specific data values, okay? So for ungrouped values, okay?